By the late 1970s, Japan had long lived under the threat of earthquakes, tsunamis, typhoons, and a restless sea. The engineers who began Seto-Ohashi had none of today's digital positioning, computer-controlled lifting, or real-time monitoring systems. With mechanical instruments, immense physical labor, and unbreakable determination, they attempted a road and rail crossing unlike anything Japan had built before. How did they complete it, and what ordeals stood between the first survey and the final span? Now rewind to the Seto Inland Sea, before surveys, foundations, towers, or cables had disturbed these waters. The project would cross western Japan's inland sea, linking Honshu with Shikoku through the Kojima-Sakaide corridor. Instead of one bridge, engineers planned a continuous route across islands, straits, and active shipping lanes. 6 major bridges would combine into one road and rail system, each structure selected for its local span. Suspension, cable-stayed, and steel-truss designs divided the immense crossing into technically manageable sections. Road traffic would run above, while 2 railway tracks passed through the deep steel truss below. Every foundation, tower, cable, and deck lift had to follow a tightly coordinated marine construction sequence. Years of fabrication, transport, surveying, and offshore work were synchronized before the first complete route could emerge. The first crews entered the corridor to measure water depths, currents, tides, and safe navigation limits. Current meters descended into the sea, recording forces that would control every tow, lift, and foundation operation. Survey vessels traced systematic lines across the corridor, converting an irregular seabed into a precise bathymetric map. Boring platforms were fixed above selected sites, allowing drill strings to penetrate sediment and underlying rock. Core barrels recovered continuous samples, revealing weathered layers, fractures, and the strength of deeper foundation rock. In the laboratory, engineers compared every core segment before deciding where immense marine foundations could safely rest. Survey monuments on the islands created a control network linking offshore measurements to one exact bridge alignment. As thousands of readings accumulated, the invisible seabed became a coordinated 3-dimensional construction plan. Drilling rigs opened blast holes through the hard, weathered rock, covering each future foundation footprint. Small controlled charges fractured the seabed, while safety zones protected nearby shipping, homes, and industrial facilities. After detonation, suspended sediment slowly cleared, revealing broken rock ready for heavy mechanical excavation. Ultra-heavy grab buckets drove their teeth into blast fractures, prying loose massive blocks from the seabed. Cycle after cycle, dredgers removed fractured rock while survey checks prevented excavation beyond the designed foundation level. A large-diameter finishing machine trimmed remaining high points and exposed a flatter, cleaner bearing surface. At depths near 50 meters, engineers personally inspected the dark rock face under powerful underwater lights. Only after strength, cleanliness, and flatness were confirmed could the foundation bed be formally accepted. Meanwhile, shipyards fabricated enormous steel plates that would become the walls of floating foundation caissons. Inside each caisson, dense cellular bulkheads created buoyancy, stiffness, and compartments for later underwater concrete filling. Before launch, inspectors checked every weld, watertight division, dimension, and closing plate against the design. The dock flooded, and the completed caisson floated free, as carefully controlled ballast maintained its stability. 12 tugboats formed a coordinated convoy, towing the giant caisson only during a long, stable weather window. The convoy moved slowly through active navigation channels, with safety vessels controlling traffic and tow line clearance. At the foundation site, mooring lines pulled the caisson toward its surveyed position above the prepared rock. Seawater entered selected compartments, lowering the structure gradually, while winches corrected drift, rotation, and tilt. During the final meters, a heavy floating crane supported the caisson and controlled its soft landing approach. The caisson settled onto bedrock within a permitted error of only 50 centimeters, forming a permanent steel mold. Large washed aggregate was then loaded into the flooded compartments, filling the interior without ordinary concrete placement. Mortar was pumped upward through injection pipes, replacing seawater inside the voids between the coarse stones. Once injection began, crews worked continuously for days, lifting the pipes as the mortar level steadily rose. Filled and locked to the bedrock, the caisson became a massive marine foundation projecting above the sea. Above water, formwork climbed around the 4A anchorage, shaping a concrete mass comparable to a large dam. Concrete was placed in controlled lifts, while temperature, curing, and reinforcement density were monitored throughout the structure. Over roughly 2.5 years, the anchorage rose through repeated pours toward its final enormous volume. Nearby shipyards assembled giant cable anchor frames, built to transfer main cable forces deep into the concrete. A 3,000-ton floating crane lifted one 1,800-ton frame above the unfinished anchorage in a single operation. Guide systems and survey teams lowered the frame into position before concrete permanently locked it inside. The completed shared anchorage contained 4 embedded anchor frames, prepared to receive cable systems from opposite directions. On each tower foundation, the first lattice base block spread immense compression safely into the concrete pedestal. Factories divided each steel tower leg into precisely machined blocks, some weighing up to 120 tons. Partial horizontal trial assembly verified joints, cross members, dimensions, and metal contact before offshore erection began. The first lower tower leg block was aligned over its base, establishing the geometry for everything above it. Compact creeper cranes attached to rails on the tower walls and climbed as erection progressed. Block by block, the 2 tower legs rose together, while surveyors continuously checked vertical alignment and joint contact. The lower cross member locked both legs together, increasing stability before work continued toward greater height. Upper blocks brought the tower close to full elevation, where wind made every lift increasingly sensitive. The upper cross member completed the tower frame and fixed the final spacing between its 2 steel legs. A saddle weighing about 150 tons was lifted immediately after the tower structure was completed. Engineers inspected saddle alignment, bearing surfaces, tower geometry, and every joint before cable work could begin. Winches, guide pulleys, and hauling lines were prepared to send the first thin rope across the channel. Because navigation could not simply close, a crane vessel kept the pilot rope continuously above the water. The receiving tower captured the pilot rope, creating the first physical connection across the open span. That slender line then hauled roughly 10 stronger support ropes into their designed sagging positions. Wire mesh and double safety netting unfolded across the support ropes, forming the first aerial working floor. The twin catwalks advanced from both sides until continuous suspended access stretched between the towers. A narrow cross bridge connected the parallel catwalks, allowing crews and tools to move between cable lines. Before strand hauling, inspectors checked floor mesh, handrails, lifelines, rope tension, and every suspended connection. At the anchorage, a giant reel carrying nearly 40 tons of prefabricated strand was mounted for payout. A hauling device pulled the first parallel wire strand above the catwalk and across the entire span. Temporary guides carried the strand smoothly over the tower saddle without twisting or damaging its parallel wires. Rollers shifted the new strand into its exact position before the anchorage socket was permanently secured. Repeated hauling cycles multiplied the separate strands, gradually building the raw form of each main cable. Inside the shared anchorage, 2 strand systems crossed at different heights without touching, a world-first arrangement. Compaction frames squeezed the accumulated strands, transforming their loose bundle into a dense, circular main cable. 2-piece cable bands closed around the compacted cable, transferring future hanger loads through controlled friction. The first hanger connection was prepared beneath a cable band, ready to support the stiffening truss below. Pairs of specialized hanger ropes descended along the span, completing the vertical support system for deck erection. For Hitsuishijima Bridge, the prepared foundation established the exact position and bearing line of its cable-stayed pylon. The first pylon segment rose from the foundation, beginning a steel frame that would anchor inclined stay cables. Successive segments extended the pylon upward, while temporary bracing and surveys preserved its geometry. The first road and rail deck segment was installed beside the pylon, creating the base for balanced erection. The first matched pair of stay cables supported equal deck lengths on opposite sides of the pylon. Deck segments and cable pairs were added alternately, keeping forces balanced as both cantilevers extended outward. Engineers adjusted stay cable tension to control deck elevation, pylon bending, and alignment before adding more segments. Repeated lifts transformed short cantilevers into a long, symmetrical cable-stayed span reaching toward closure. At Iwakurojima, access platforms and foundation work prepared another pylon within the narrow island corridor. The second cable-stayed pylon rose in stages, repeating the method with geometry tailored to its location. A deep double-deck segment was installed, carrying the future roadway above and railway structure below. Each new segment received another inclined stay, expanding the pylon's fan while controlling structural deformation. The balanced cantilevers reached farther over open water, as erection loads were continuously redistributed through the stays. When marine weather exceeded limits, the lift paused, the load was secured, and alignment was protected. The final midspan segment joined both cantilevers, converting temporary erection systems into one continuous cable-stayed bridge. With both twin bridges structurally complete, the corridor advanced toward Yoshima and the southern suspension spans. Yoshima's deep steel truss members were fabricated and trial-fitted to ensure every connection matched offshore geometry. Piers, bearings, and access systems were prepared to receive heavy truss blocks along the curved island crossing. The first deep truss block rose from a barge and settled precisely onto its prepared bearings. Additional blocks extended the truss over water, with temporary bracing stabilizing each new connection. Repeated lifting and assembly gradually formed Yoshima's continuous steel truss route across the island channels. The final closure member joined both advancing sections, completing the continuous structural load path. Upper deck panels created the roadway level above the deep truss, ready for waterproofing and pavement. Below, railway deck structure and track supports were installed inside the truss, with strict alignment control. At Kita Bison Seto, the first large stiffening truss block was lifted near a tower to establish bridge-level workspace. Two-panel erection cycles extended the truss, while crews balanced progress and monitored changing main cable geometry. At Minami Bison Seto, heavy lifting resumed only after wind, current, and vessel position returned within limits. Jacks adjusted the approaching truss ends, allowing the final midspan closure panel to enter safely. Shimotsui Seto reached structural closure, completing the last major suspension span across the northern channel. Crews installed pavement, railway track, expansion systems, utilities, weather instruments, and traffic control equipment across the route. Loaded vehicles and controlled vibration tests measured deflection, structural response, and the accuracy of the completed design. A test train approaching 1,000 tons verified ride quality, track behavior, and stability before opening. In daylight, 6 great bridges finally formed a continuous 13-kilometer road and rail crossing between Honshu and Shikoku. After 9.5 years, Seto-Ohashi opened on April 10, 1988, an extraordinary victory of engineering and endurance.